Okay, now we consider improper integrals of type 2. So first, let's take a look at this, the graph of the function f of x equal 1 over x minus 1. Suppose that I would like to have the integral from, let's say, minus 1 to 2 of 1 over x minus 1 dx. Okay, so it's wrong, so you have to be very careful. It's wrong to do this as ln absolute value of x minus 1. That's the antiderivative of this from negative 1 to 2. And then you got ln of 2 minus 1 is absolute value, sorry, of 2 minus 1 is 1 minus ln absolute value of minus 1 is absolute value of negative 2, so that's 0 minus ln of 2. This is wrong. Okay, the reason is this wrong. First, you do have discontinuity, an infinite discontinuity on the interval from negative 1 to 2, and that's the interval from negative 1 to 2. It's right here. Let's say this is minus 1, this is 2. So what I'm trying to find really here for this definite integral is the following area. See this area right here? This is going to keep going. The area right here up to this line, and this is going to keep going up. So it looks like I have like two unbounded regions that I'm trying to find their area. So the fundamental theorem of calculus part 2 is not applicable in this case because you have infinite discontinuity at 1. So the function f of x is discontinuous at x equal 1. And the type of discontinuity here again is infinite because the limit of f of x when x approaches 1 minus or 1 plus is infinity. At 1 minus it's negative infinity, at 1 plus it's positive infinity. So what do we do in this case? Well, in this situation, the idea is the following, and that's how we're going to be treating, this is a type 2 improper integral, so that's how we treat it. I know that the problem that I have is at 0. So what we do is we find the integral first. So integral from negative 1 to 2 of 1 over x minus 1 dx. This is the integral from negative 1 to 0, 1 over x minus 1 dx, plus the integral from 0 to 2 of 1 over x minus 1 dx. So this integral has a problem at, 1, because the 1 is it's where we have discontinuity. I mistyped this here, so this is 1. Okay, so from negative 1 to 1 and from 1 to 2. Both integrals have problems at 1. Okay, so we have to, what do we do in this case is we try to find each integral by itself and see and add them up. If they are both convergent, then I will be adding two finite numbers. I will get the finite number. I will be fine. If one of them is divergent, then we stop and we claim that the original integral is divergent. Okay, so here, for example, let's say that I want to do this integral. Okay, so integral from 1 to 2 of 1 over x minus 1 dx. Now, how do we do this one? Well, the problem that what we have right here is the at 1. So what I do is the following. I pick a number r close to 1. And then I find the integral from r to 2. Okay? So the red region corresponds to the integral from r to 2 of 1 over x minus 1 dx. This is an integral that I can find using the fundamental theorem of calculus because 1 over x minus 1 is continuous between r and 2. So this is going to give me an answer. This answer is going to be in terms of r. In fact, I can finish this. This is equal to ln absolute value of x minus 1 between r and 2. Okay, so first let me write the limit. So that's the limit when r goes to 0. Again here, I'm gonna let r approaches 1. And because r is approaches 1, this is gonna approach 1 from, it's approaching 1 from the right, so that's gonna approach 1 plus. So that's how I write my integral. Integral from r to 2, 1 over x minus 1 dx. So this can be evaluated right now. This is the limit when r goes to 1 plus ln absolute value of x minus 1 between r and 2. So this is limit when r goes to 1 plus ln of absolute value of 2 minus 1 is ln 1 minus ln absolute value of r. ln 1 is 0 minus. Now ln of r when r minus 1. ln of r minus 1 when r goes to 1 plus is like ln of 0, and this is negative infinity. So the answer is positive infinity, meaning that the integral is divergent. Okay, so this tells me the following, that this area right here, the green one, the red one, when I will take it to positive, when I will take the limit when r approaches 1 plus, this is going to give me this area, the green one, and this is equal to infinity as we computed. This means that this integral from 1 to 2 is divergent, and so is this integral from negative 1 to 2. So this is the idea of improper integrals of type 2. That's how we're going to deal with it. And here's the formal definition. So suppose that I have an integral from a to b of f of x dx, and f is discontinuous at one of the endpoints, a or b. So if it's discontinuous at a, that means it's continuous on the open interval a to b. So it's continuous on this piece, a to b. So what do we do in this case? Like I did in the previous example, you compute, you pick a number r here between a and b, you compute the integral from r to b, and then you're gonna get something in terms of r, and then you let r approaches a plus. So as you can see here in this definition, that would be the limit when r approaches a plus, integral from r to b of f of x dx. Now if the situation is that f is continuous on AB, that means f is not continuous at the right endpoint. Okay, so you have the following problem. F is not continuous at B. So you pick again a variable r between a and b. You compute the integral from a to r, which can be always found. This is going to be an expression in terms of r, and then you will let r approaches b. This is going to approach b from the left, so that's why you have limit when r approaches b minus of the integral from a to r of f of x dx. If the limit above exists and is finite number, we say the improper integral converges. Now remember that when we say the limit exists, that means it's a finite number, or if you have a limit and it's infinity, that means it exists. But here we are saying that is finite, so we are removing the case of plus minus infinity. And we are putting the case of plus minus infinity under the divergent part. So if you got plus minus infinity or limit does not exist, then we say that the integral is divergent. Okay. Now, if you want to compute the integral from a to b, and let's say the function is discontinuous at a point c inside, like the example I just did at the beginning. I was trying to compute it between an interval -1 to 2, and then it was discontinuous at 1. So what do we do in this case? We split the interval, like the integral over the interval, like I did in the example. So we find the integral from a to c and then from c to b. If both integrals are convergent, then this integral will be convergent. If one of them is divergent, if at least one of them is divergent, then the original integral will be divergent. Okay? So this is what we just explained here graphically. That's what it means to say that the integral from a to b of f of x dx equals the limit of f of x of the integral from r to b of f of x dx when r approaches a plus. So let's consider the following example. This is an improper integral of type 2. You can see that the discontinuity is at 0. So the integral from -1 to 1, 1 over x squared dx. This is the integral from -1 to 0, 1 over x squared dx, plus the integral from 0 to 1 of 1 over x squared dx. Now I have to compute these two integrals. Both of them are improper integrals because they're not continuous at 0. So I will take, for example, that one and try to do it first. If this ends up to be divergent, then my answer will be that the integral from -1 to 1 of 1 over x squared dx is divergent. Now, by the definition that we gave in the previous slide, that would be the limit when r approaches 0 plus integral from r to 1, 1 over x squared dx. So this is the limit when r approaches 0 plus. The antiderivative of 1 over x squared is -1 over x between r and 1. Okay, so this is the limit when r goes to 0 plus. -1 over 1 minus -1 over r. So this is the limit when r goes to 0 plus -1 plus 1 over r. Now -1 is a constant, so that would be just -1. Now 1 over r, this has the form when r goes to 0 plus as 1 over 0 plus. 1 over 0 is infinity. 1 over 0 plus is positive infinity as well, so that's just infinity. So this means that the integral diverges as a result. Here's another example. Determine if the integral from 2 to 5 of 1 over x minus 2 dx is convergent or divergent. Evaluate if it's convergent. So again, here I have a problem at 2. Okay, so the denominator is radical x minus 2. X cannot be equal to 2. So the integral from 2 to 5, 1 over radical x minus 2 dx, that's an improper integral of type 2. I can write this as limit when r goes to, so here r to 5, and r is going to approach 2 from the right, 2 plus 1 over radical x minus 2. Okay. Now the integral of this one, you can use the formula that we gave in a previous slide, like 1 over ax or ax plus b to the power n, because this can be written as x minus 2 to the power negative 1/2. But if you don't have the formula or you forgot, you can simply compute this by substitution. So if I want to find this integral, I can let u be x minus 2. So then du is equal to dx. So my integral becomes integral 1 over x minus 2 dx equal integral 1 over radical u du. Okay, so this is integral of u to the power negative 1/2 du, which is u to the power 1/2 over 1/2 plus constant, so this is 2 radical u plus constant. Now, using this here, this is going to be limit when r approaches 2 plus. The antiderivative, as we said, it's 2 radical u, which is actually 2 radical x minus 2. So that's going to be limit when r goes to 2 plus 2 radical x minus 2 between r and 5. So this is limit when r goes to 2 plus 2 radical 3 minus 2 radical r minus 2. When you let r goes to 2, this becomes 2 radical 3. You can do just direct substitution here. 2 minus 2, so the answer is 2 radical 3. That's a finite number. So I conclude that integral from 2 to 5 of 1 over radical x minus 2 dx is convergent, and actually it's equal to 2 times radical of 3. Okay, well, what does this mean graphically? Let's take a look at the graph of 1 over radical x minus 2 first. Okay, so this is how the graph looks like. That's the graph of 1 over radical x minus 2. And at x minus 2 over here, we do have like a vertical asymptote. Okay, so there's a vertical asymptote here at x equal to. So we were looking for the integral from 2 to 5. So let's say 5 is over here. So the integral from 2 to 5 is this area. Notice that this area is unbounded. Okay, this region is unbounded because that's gonna keep going to between the curve and x equal to. Even though it's the curve and x equal to, you can see that how close they are early. Well, this area actually is 2 radical 3. Although the region is unbounded, the area is finite. Okay, this is something really nice here. Now we're gonna take a look at p integrals.